Good morning. Today we're going to finish off the rest of section 8.7. The last thing we need to talk through in both section 7 and for the entire chapter is a formula, and it's called the binomial experiment formula. And it's a formula that's going to allow us to calculate probabilities in a situation where we have a situation which is binomial, all right? Meaning there's only two possible outcomes. Only two possible outcomes. So could be something as simple as heads and tails. Those are the only two options. As opposed to rolling a die, where when we roll a die there's six possible outcomes. Heads and tails, there's only two, so we could use it for something like that. The situation we're going to use, though, for our examples, we're going to have you guys taking some tests, and we're going to start with true-false tests, and we're going to move on to multiple choice tests, and we're going to use the formula to calculate the probability that you get a certain number of questions right on a true-false test or multiple choice test by applying the formula. Okay? So let me first give you the formula, and then I'll explain how we can use it. All right, so we start with P for probability. Now, what we're taking the probability of are what are called successes. So we're going to calculate the probability of K successes in N trials. So the trials would represent the total number of questions on your test as an example. Okay? And so the two letters I need you to keep track of, let me highlight them in a color here. So I need you to keep track of the K, and I need you to keep track of the N. Okay, N is going to represent the total, and K represents the number of successes that we're calculating the probability for. Okay, so here comes the formula. It's going to be the number of combinations of N taken K at a time. So you can see where the N and the K came from, times little p, which I'll explain to you in just a second, raised to the K power, times 1 minus p raised to the N minus K power. So you can repeatedly see both the K and the N in the formula, but what we're missing now is what in the world is little p, and little p is the probability of a success, which means 1 minus little p would be the complement of that. Remember complement from earlier in the chapter, and the complement 1 minus p would then be the probability of a failure. All right, so we have capital C, which stands for combinations, which we've already talked about, all right, times probability times the complement 1 minus p, right? And when you put all of these together, we get what's called the binomial experiment formula. Alrighty? Now, please pause the video to make sure you get that onto your help sheet somewhere. And once you have a chance to get that on your help sheet, move on to the example questions. The first example question is going to be the following. You take a true-false test, and the test is made up of 8 questions. Now, what we're assuming is that you don't study, you don't read, you don't pay attention, you're just going into this test and you're going to randomly guess the answers, and maybe not even looking at the questions. You're just going to randomly select true, false. What I'm going to ask to start with is what's the probability that you pass? And in our school, passing means let's see, we'd need 60%, so I guess that would be 5 correct. Sorry about that. So passing for our school would be 5 correct out of the 8 questions. So what's the probability that you get 5 correct? Well, since we're looking for 5 correct, that's what we call a success. So 5 is going to be the value of K. The total number of trials represents the total questions here, so that's going to be the 8. So we have a couple of our values already. We have our N value, our total number of questions, our K value, the number that we're trying to get correct. Okay? So what the formula says is we take the number of combinations of n, total number of questions, our number of successes, we're trying to get 5 correct, so it'd be 8C5, times the probability of a success raised to the k power, so that'd be raised to the 5th, times the probability of a failure raised to the n minus k, so 8 minus 5, or third power. Now, what's the probability that you get a true-false question correct without studying, without reading? What's the probability of getting a true-false question correct? The answer is 1/2. Now, if the probability of getting one correct is 1/2, what's the probability of getting one wrong? Well, that would also be 1/2. So we need 3 values. We need the number of combinations of 8 things, selected 5 at a time, so 8C5 is 56. I just used my calculator to punch that out. We need 1/2 raised to the 5th power, which would be 1/32. We need 1/2 raised to the 3rd power, which would be 1/8. And when we multiply those together, what we get is 56 on top of 256. All right? Now, I'm not sure what's going to cancel. I think I can cancel a 4 for sure. Yep. So if I canceled a 4 in the top and a 4 in the bottom, I believe I get 14/64. And if I punch that out as a decimal for everybody, we'll get about 0.22. So another way to think of that is you'd have a 22% chance of randomly guessing 5 correct. Okay? What if 5 correct isn't good enough for you? What if you wanted to get 7 correct? What would be the probability of randomly guessing 7 problems correct on our true-false test? All right? Well, I'll set it up and then I'll move the screen here to show you the rest of the computation. So 7 now becomes the k value. That's the number of successes we want to have. So the formula then says, well, we'll take the number of combinations of 8 total questions. We want to have 7 successes, so 8C7, times the probability. All right, so we have 8C7, right? And then we have the probability of a success raised to the k, or 7th power. And we have the probability of a failure raised to the 8 minus 7, or 1st power. All right, so if I slide this up, I can show you that 8C7, is that going to be an 8? I'm doing that right in my head. I'll double check on my calculator. I'm going to screw that up. Yeah, so that's an 8. And then I'll have 1/2 raised to the 7th power, which is 1/128. 1/2 to the 1st power, which of course is just 1/2. And when I multiply these folks together, I get 8/128. And what can I cancel top and bottom there? I think I can cancel an 8, right? Am I doing that right? Yeah. And so we'd have 1/16. And 1/16 as a fraction, if anybody's curious, would be 0.0625. 0.0625. So the probability of getting 7 correct on a true-false question, true-false test with 8 questions, probability of getting 7 correct, which is what, B plus or something like that, would be 1/16 or 0.0625, so not very likely. Okay, then I'd like to change gears just for another example. I'd like to change gears a little bit and go from true-false to multiple choice. Okay? I'm not sure how many multiple choice tests you guys take outside of like MCAs and all of that stuff. But we're going to have a multiple choice test where every question has 4 options. Okay, 4 options, so we'd have like a B, C, D on every question, that sort of thing. And our test is going to have 6 questions. So we're going to have 6 multiple choice questions on this. Let's call it a quiz. Okay? Now, how does multiple choice change the way we apply the formula? Well, let's work through. So for our 6 questions, let's find the probability. What would be the best passing grade there? Let's say that we would get 4 correct. Okay, what's the probability again, without any studying, without any reading, just taking a stab in the dark, what's the probability that you'd get 4 correct? So 4 then becomes our number of successes. So let me highlight that like I was doing before. So that would be the number of successes. And our total number of questions then is 6. That's the number of questions that we have overall. Okay, so that's our trials. So we have our n value, we have our k value, and now we just apply the formula. So this would then be the number of combinations, 6 total things, and we want to have 4 successes. So 6C4 times the probability of success raised to the 4th power times the probability of a failure raised to the 6 minus 4, or 2nd power. Okay? Now, what really changes when we go from true, false to multiple choice is the probability of success. Because we're multiple choice, A, B, C, D, now the probability of guessing one correct isn't 1/2, but it is 1/4. All right? And if the probability of a success is 1/4, the probability of a failure is 1 minus 1/4, or 3/4. Okay? And so now we could just punch out the 3 pieces. We could punch out 6C4, which is 15. We could punch out 1/4 to the 4th power and 3/4 to the 2nd power. 3/4 to the 2nd, no sweat, I got that. But 1/4 to the 4th, I think, is 1/256. Let me double check that though, so I don't screw that up. Yeah, so 1/256. Okay, and so when we multiply 15 times 1 times 9, I would have 135. And when I multiply 256 times 16, I get 4,096. 4,096. And when I punch that out as a decimal to give you a feel for how small that is, we would be at 0.033, 0.033. Or if you change to a percent, you'd have about a 3.3% chance of getting 4 correct. All right, 3.3% chance, if you didn't study, didn't pay attention, didn't read, of getting 4 out of 6 questions or getting a passing grade. Okay? Let's do maybe just a couple more quick with the same setup. 4 options, A, B, C, D on the multiple choice, and 6 questions. So let's go with the smaller amount. How about the probability of getting 2 correct? All right. So now our number of successes, our k value is 2. Our n value is still 6. We still have 6 total questions. So the probability will be then 6C2, 6 total questions. We're trying to get 2 correct, times the probability of success. Once again, that's going to be 1/4 raised to the 2nd power. And the probability of a failure, 3/4 raised to the 6 minus 2, or 4th power. So 6C2 is going to be 15 again. 1/4 raised to the 2nd power is 1/16. 3/4 raised to the 4th power is going to be, that's a 256 down in the basement. And 3 to the 4th is what, 81 up top. And so when I multiply 15 times 1 times 81, we get 1,215. And down in the bottom, I forgot what that was last time. Sorry, 4,000? Yeah, 4,096 down in the basement. Okay, so when you punch that out as a decimal, you can see your probability is much better of getting 2 correct. The probability would be just a hair short of 0.3, which of course would be 30%. So you'd have a 30% chance of getting 2 correct. Of course, that's not passing, but you'd have a pretty good probability of guessing 2 correct. And let's just flip it on the other side. Let's flip it on the other side. Let's get a bunch. In fact, how about if we get them all correct? What would be the probability of getting all 6 correct? Okay. Well, again, this then represents the number of successes, k. So our formula says that this is going to be 6C6 okay? Times the probability of success raised to the 6th power, the number of successes, times the probability of a failure raised to the 6 minus 6, or 0 power. All right? And so what we'll end up with is 6c6, which is a 1, 1/4 to the 6th, which is 1 over 4,096, and 3/4 raised to the 0 power. Remember, anything to the 0 power is 1. So when we multiply 1 times 1 times 1, we get 1 over 4,096. And as a decimal, that would be 0.00024. Or as a percent, let me sneak it in there, that would be 0.024%. Okay? So not very likely that you're going to get all 6 questions correct unless you study a little bit. Okay? Alrighty. So that finishes off the rest of section 7. So I'll be back tomorrow. We're going to go over questions on this one, turn it in. Then we're also going to do a chapter review, and we'll be taking our chapter, 8? Yeah, chapter 8 test on Friday. So hope you're having a good day, and we'll see you tomorrow. Bye.